Thank you. Good afternoon. Welcome, London. Great to be here. I was born here, but I've been in Edinburgh since '86, so I guess I'm not really a Londoner anymore. If anyone does want to follow along, there's a URL up there, and I put it in the Slack, which has got the slides. There are an intimidatingly large number of slides, more than one a minute, but we're going to skip right over a lot of them. We have got a lot to get through. I probably will talk a bit too fast, but I've left quite a lot of material in there that hopefully you can use as reference afterwards if you want to. You can follow along as I'm doing stuff if you've got the library installed, and if not, it'll be there for later. So the rough outline is I'm going to talk for probably about 20 minutes about the methodology and motivation of what I call test-driven data analysis, or sometimes test-driven data science. Then I'll talk about specifically checking data with constraints using the TDDA library. And if we have time, I'll talk about inferring regular expressions from examples, which is one of the superpowers of the library. Then I'll start talking about testing analytical code with, again, support from the Python open source TDDA library. And if we have time, I'll talk about automatic test generation with GenTest, but we really might not have time for that. And at the end, I'll talk about type 6 errors. And I'm going to, for those of you who don't look at the slides, I'll reveal what type 6 errors are later. Obviously, we have to check that our timings work out, and they do. They sum to 90 minutes. But that's not very good news because we've only got 90 minutes. So I'll try not to gobble. So I'm sure many of you know and use or will have used test-driven development, TDD. But for those of you who aren't familiar with it, the idea with test-driven development is that when you want to write some functionality, you want to write, it could be an addition function or it could be the most amazingly complex thing. The first thing you do is not to start writing code or indeed to write a functional specification or a design document or any of that waterfall stuff. You start off by writing some tests. And there are test frameworks, like with Python, unit test comes in the standard library, and there's PyTest that a lot of people like, that allow you to run your tests before writing any code. And if you run them at the start and you call your add function that you haven't written, they will raise an error. You'll get an E typically for every test that fails. And then the idea is that that acts as a specification and an API design, and you start writing code to make the tests pass, and you have a sort of negotiation between the tests and your code, depending on whether you're better at writing code or writing tests. You might find that you have to adapt your tests because actually your code was better than your tests, or vice versa, or a bit of both. And then the idea is that as soon as you get all the tests to pass, you stop, because the tests acted as a specification for what your code was supposed to do. And the only thing you do after that is you simplify the code. You make it more elegant, you make it more general, what's called refactoring in the test-driven world. The idea there being that it's much easier to write correct code that's simple and ugly, and then when you have confidence that it's passing, you can make it better, and as long as the tests keep passing, you have a high degree of confidence that you haven't broken your code. And then the next part is that if you find bugs, the first thing you do isn't rush off to fix the bug. You first of all write a test that exhibits the bug, and then you write code to fix that. And similarly, if you want to write new functionality, you first of all write tests, and you keep on doing this. And in the modern world, the idea is then with these tests that you run them continuously, whatever continuously means. And that can either mean you run them by hand every now and again, particularly when you make changes, or these days it can mean you have a continuous integration framework that runs them for you. GitHub has GitHub Actions that will do that for you, or you can use something like Jenkins or whatever. And in the case of conventional software development, this is all happening often in the context of well-understood inputs, a clearly understood goal, and a lot of the time, lots of kinds of errors and failures are fairly obvious. Not all the time, obviously, you can have subtle bugs, but and so that's test-driven development. And what happened about 10 years ago was my best ever student and colleague, a guy called Patrick Surrey, came in and said, Nick, you know how you crap on all the time and insist we do this test-driven data stuff? What about test-driven data analysis? Shouldn't we do that? And we sort of looked at each other, and it was immediately completely obvious that, of course, we should do that. The only problem was we had absolutely no idea what test-driven data analysis could possibly mean. And really, the journey of the last 10 years for me has been trying to work that out. So I don't know about you, but I've worked on a lot of data analysis projects. I've seen a lot of data analysis going on, and it doesn't look quite like test-driven development. It looks a bit more like this, where someone kind of chucks you some data and a very vague specification of a problem and says, see if you can figure out, what's going on with this. And, you sort of catch the data and eyeball it, and you start, segmenting it and profiling it. You discover that the data doesn't make any sense at all. It doesn't even seem to be about the same domain as you're being asked about. And so you curse Microsoft a bit, and you go back and try and resource the data, and you ask the experts. And, this whole thing goes on, and it's all this complete mess. And eventually, in the good case, you start to generate some results. And you look at them, but they don't make sense, so you have to go and fix everything. And eventually, maybe you get to the stage where you start to believe things, and maybe you show it to someone else and they start to believe things. In the really good case, maybe you get to the point where you feel confident enough to share it and deploy it and use it or whatever. And in the bad case, you give up and go on to the next project and catch your next bit of data. And, maybe that's just me, but that's what I see a lot in this world. And so really the conceptual idea of test-driven data analysis is, wouldn't it be nice if we could take this idea from the world of automated testing, test-driven development, and make that appropriate for data analysis and carry over this idea of testing for correctness, but also test for the other sorts of things that we ought to care about as data analysts, data scientists, data engineers, data professionals, whatever we want to call ourselves, like the meaningfulness of the analysis and the correctness and validity of the input and output data. Wouldn't that be nice? And correctness of interpretation. That one's quite tough, but I think we have to take responsibility for that as well. So that's what we're going to try to do. Oh, yes, my friend Jeremy. So some of you will remember Jeremy Paxman, either from University Challenge, where he tortured my son, who captained the winning Durham team last year, in fact, but possibly as a famously aggressive political interviewer. And he was asked one day, well, what do you think? When you're interviewing a politician, what's going through your mind? And what he said is, what's just going through my mind the whole time on a loop is, why is this lying bastard lying to me? And he later recanted that a bit and all the rest of it. It turned out he nicked it from Louis Heron anyway. But what I'm doing all the time when I'm doing data analysis, and what I would strongly recommend you do all the time when you're doing any kind of data analysis or processing, is the whole time you're thinking on a loop, how is this misleading data misleading me? Because believe me, it probably is misleading you. And the nicer the output looks, the more likely it is you're seduced by that beautiful looking output. So test-driven data analysis is both a methodology for attempting to improve data quality and the quality of analytical processes, data pipelines, whatever you want to call them, sort of thing that Juan was talking about previously. And it's also an open source library that encapsulates a lot of those ideas, some of which is specific to Python. The software testing bit's somewhat specific to Python, except for the automatic test generation bit, which is actually for any software. The data checking bit is actually potentially suitable for anyone. I know we're at PyData, but I bet there are some non-Python people here, so it's potentially relevant for you too. And there's a commercial version that my company produces as well that is a bit fancier on the data checking side, but we don't need to worry about that today. So, so here's the slightly more structured form of what I think data analysis projects tend to look like these days, which is data analysis always happens in the context of a real concrete data set. It's almost never the case that you just start writing code without having some data to run through whatever your processing is. And if you are in that situation, you almost always frig some up. Sorry, did I say frig some up? You almost always synthesize some data of the right shape to run through your pipeline. And in the development phase, there are two major things that you have to do, both of which can go wrong. The first is that you have to choose your approach to solving the problem. And the sorts of things that can go wrong there are you can fail to understand the data, or fail to understand the problem, or fail to understand the libraries, or fail to understand the methods or the domain or something like that. And when that happens, I call those errors of interpretation. Okay? Sometimes errors of formulation, but in general errors of interpretation. And the other thing that can happen is when you develop your actual analytical process. Well, if that's software, you can have bugs in it, errors of implementation, if you like. But also I'm thinking about processes that aren't necessarily fully scripted. So maybe you've got instructions for downloading a data set from here and putting it into Excel and whatever, and there can be mistakes in that as well. And you only get the right result on your initial sample of data if you don't make a critical mistake in one of those two areas. It's fine if you make some mistakes. Almost certainly you're not writing software without bugs. But if you make a critical mistake in those areas, by definition, you get failure. But then, there's usually, these days, an operational phase. And there are a whole new set of things that can go wrong during the operational phase. Someone has to run the code, or you have to automate the code. And at that point, you can use the software incorrectly, right? You can type the wrong parameter, or you can fail to follow the procedure properly, errors of process. A more subtle one is there can be a mismatch between either what was true of the data you initially analyzed or what was true of the world at the time you analyzed that initial data and the world now. Maybe the world will be different. Oh, there you go. Maybe the world will be different after July the 4th. Or maybe it'll be exactly the same. And if that happens, I call those errors of applicability. So you built a perfectly good model that was good on your data, but maybe you built it in England and now you're applying it in Uruguay. Or you built it in 2023 and the world is different in 2024. What used to make people a good credit risk doesn't make them a good credit risk anymore, or whatever it happens to be. So errors of applicability. And finally, the bit that people always forget about is that someone has to interpret the results typically at the end of it, and that can go on. I'm not talking about subtle misinterpretations. I'm talking about really fundamental misinterpretations, like, you know, you're modeling airline safety or something, and you come up with a number 99.99999%, and you think, great, I'll get on the plane. But that was the probability of its crashing, not the probability of you having a safe flight, and that's quite a big misinterpretation, an error of communication, if you like. And so we only get success when we run data through the pipeline if we haven't made a critical mistake at any of those phases, right? And the really bad news is that then we go around and pass more data through it in the operational phase, and we've got a chance of going wrong every time. So if your process looks anything remotely like this and you buy into this model, it's really quite sobering, I would contend, to put numbers on it. So I've put what I think are incredibly optimistic numbers on the chances of not making a critical mistake at each stage. I'm assuming that there's only a 20% chance of fundamentally misunderstanding stuff at the start, only a 30% chance of a critical bug, only a 10% chance of an error of process, only a 20% chance of the world having changed, and only a 10% chance of the answer being misinterpreted. And if you buy those numbers, and maybe you're much better than I am, and you know, all your numbers are 95% or whatever, but if you buy these numbers, you've only got a 36% chance of getting the right answer out the first time through. And your chance of not having had a critical failure if you run it through half a dozen times is, you know, even worse than that. It just goes down. So this is why we're trying to make things better. So the main ideas in TDDA, the two things that I'm going to talk about mostly in this talk, are first of all the use of constraints to check data, and that's not new, that's how people always check data. But what is slightly new is the idea of getting the machine to help you figure out what the right constraints are, which is what's a bit clever in the library. This can cover and should cover inputs, outputs, intermediate results. As I say, they can be automatically discovered or generated, though they should then be refined by humans ideally. And the second part of TDDA, the second major part of TDDA, is for checking analytical processes, analytical pipelines with what I call reference testing. And reference testing is just automated software testing, but adapted to the world of data analysis where the standard TDD approach is a little bit challenging, basically because our outputs are so big and complex, even in small cases often. And so there's lots of assistance for writing practical tests, partly with automatic code generation, but mostly through just giving you really nice extra assertions and stuff like that. So that's what we're going to go through. You've either got the library or you haven't. You can just pip install it with pip install TDDA or whatever the correct incantation for your setup is. You can get it from source if you want. It's MIT licensed. It runs on all the things. Well, it doesn't run on Python 2 anymore, but it did until quite recently. It's documented. And you can think of the library as being like three machines. The first machine is a machine which in one mode you feed data into, and it spits out constraints that are true for that data or nearly true for that data. And then in the verification phase, you feed in those constraints plus a new copy of the data or a new version of the data, new data, and it spits out verifications. It tells you whether the data passed, and if it didn't pass, which parts failed and how they failed. There's an enabling bit that turns out to be quite useful in its own right, which is called RexPy, which also comes with it, which is for generating regular expressions from example data, because those of you who've used regular expressions will know it is possible to get them wrong. Probably not for you, but for people like me. And then the final part, which mostly isn't a machine, it's mostly just a set of extensions for PyTest and unit test, but is this idea of reference testing. But it can, and so that's an API that you use to write tests more easily, appropriate tests more easily. But there is also this embryonic, this experimental gen test capability where you literally feed in code and it spits out tests. It writes tests in Python, but they can be tests for a shell script or an R script or some SQL or whatever. It's not doing GUIs or anything like that yet, but you know, proper command line stuff. Okay, how are we doing? That was supposed to be 20 minutes. My God, we're ahead of schedule. I don't believe it. Okay, constraint identification and verification, the first machine. So, before we do that, I have to talk a little bit about GIGO. You all know GIGO, right? Garbage in, garbage out, a phrase that annoys me intensely because it's like, well, it's not my fault. I wrote perfectly good software. You feed garbage in. What do you expect? It's like, that is normality, but it's complete negligence. I think that data scientists have to try better than that. We have to be trying, at least, to do error detection and to notice when garbage gets fed in. Now, we can't always do that. Sometimes the garbage is really, really well disguised and very hard to distinguish from ordinary data. But it's just irresponsible not even to check it and not even to throw a warning or an error or whatever's appropriate if you notice it. And TDDA's, the checking part's mostly about trying to achieve that. There is something even better than error detection, which is garbage in, gold out. So if you can safely correct the data, because it just requires normalization and standardization and all that kind of stuff, then you can actually send out better results or better input, a better copy of the input data than came in. But there's also one thing that's even worse than garbage in, garbage out, which is the other GIGO. So TDDA basically tries to do the orange one. It to some extent helps with the green one and to some extent with the blue one, but mostly it's about error detection. But the thing that's even worse than that is gold in, garbage out, where because you write such shitty code, sorry, I shouldn't swear, because you write such poor code, gold comes in, perfectly good data comes out, and you produce complete nonsense at the end. The sort of thing LLMs, no, I mustn't say that. Okay, so I think data workers, data professionals, whatever we want to call ourselves, we should sign up to the actual Hippocratic Oath, right? First, do no harm. Do not take in nonsense or take in good stuff and turn out nonsense. So, constraints. This is mostly in the context of, tabular data, structured tabular data, columns, with consistent types and rows and all that sort of stuff, the usual stuff we work with, data frames, if you like, for inputs and outputs and intermediates. It can be extended to other things, but that's mostly where it is. And when we're working with that, there are usually lots of things that we know or expect to be true about our data. And what we could do, and what we traditionally do, and if it's sufficiently important, maybe we do, is we could sit down and we could write them out and say, well, if it's an age, it ought to be an integer, and it probably shouldn't be negative, and it, whatever it happens to be. But life's too short. People don't really enjoy doing that, and actually, humans are rather error-prone, and except for some very special individuals, they're not actually very good at it. So the big idea is to use more of a machine learning kind of a setup, not necessarily machine learning per se, and give the computer some training data that ideally is known good data, or at very least is data of the right shape, and get it to spit out constraints that are true or possibly nearly true for that data, and then hopefully to validate those constraints, to look at them and check that they seem sensible, and then start using them in production. So, what are the sorts of ages? Well, there are single field constraints, so if it's human ages, they almost certainly shouldn't be more than 150. They probably shouldn't be negative. They should probably be whole numbers. If you've got a customer ID, it's usually a bad thing if that's null. If you've got a customer table with a customer ID, it probably ought to be unique. If you've got a credit card number, it probably, all sorts of simple stuff like that and more complicated stuff than that. There are also data set level constraints. So maybe the field, the frame has to have a customer ID field, and maybe it has to have a particular number of records, or maybe it should be sorted ascending by date or whatever. And there are also multi-field constraints. So if you've got an open date and a close date, it's normally not good news if the open date's after the close date. And with I don't know if there's anyone born on the 1st of January 1970 here, but normally the 1st of January 1970 is a date that you want to be very careful about. So those are the sorts of things. And so I guess I've said this, but the idea is you use this machine learning type setup where you have some training data, ideally data that you've checked by hand and you believe to be good, but it doesn't have to be perfect. You throw this into the, this engine, and it spits out constraints that are true or nearly true for that data. Ideally, now you look at those constraints and you check them by hand. Maybe you even use some holdout data as well and verify some new data with it. And well, that's the start, and let's go. So if you've got it installed, I'm not going to stop, but if you've got it installed, you can follow along, and if not, you can just watch me. That wasn't the right button to press. So if you do have it installed, the TDDA library comes with command line, TDDA command line, and you can just say TDDA examples in a directory where you're happy for it to write some new directories, and it will write 4 directories for you with examples for reference testing, constraints for XPy and GenTest. So we're going to look at the constraints examples. And what I've got in here, and I really should update this, but we've got a bunch of scripts and things, and in this test data directory, we've got some data. It's the periodic table as it was about 10 years ago when I produced the examples. And it's, you know, it's just some stuff extracted from Wikipedia with the atomic symbol, sorry, the atomic number and the name and the symbol and the period and the group and all that sort of stuff. It's a bit hard to read like that. So if I go into the constraints examples, test data / whatever I said it was. So it, you know, it looks like this, and it should look quite familiar. It's hydrogen and helium and lithium and, you know, symbols and all this kind of stuff. And the point about this is mostly just that it's got lots of different types and stuff like that. And it's tiny. You can use this on big stuff as well, but it's tiny. So that's the data we're going to work with. And what we're going to do, following along with the slide, is we're going to ask TDDA to discover some constraints. We discover some constraints that are true for this data. So we're going to say TDDA, discover, and we're going to say -r, and -r says, I would like you to generate regular expressions for this data. The only reason you need that flag is that if you throw this on a large data set with lots of free text data, that'll take a very long time because that turns out to be not very sensible. But normally we will want this, so, and then we tell it what data we want it to do the discovery on, which is this elements 92. So that's all the elements up to uranium, .csv. And we tell it where we'd like it to write the constraints to, and I'd like those to go to elements 92.tdda. It's going to be a JSON file, but we normally use a TDDA extension for it, so we know what it is. And it will go through and generate those, and we can have a look at them. Yes, I'm really old and I use Emacs. Not books TDDS, but TDDA course constraints examples elements 92.tdda. And so we have a JSON file that has a load of metadata that hopefully confirms that it was generated a few seconds ago at 15:53:09. And then we have a set of constraints. And some of these constraints are extremely simple, and you can see exactly how they were generated. So for Z, the atomic number, what it's basically saying is I read the file, and all the things in the Z column look like they were integers. So I'm going to say not that they are integers, but that they must be integers. The constraint's going to be this field must be full of integers. And it says, and the smallest value I found was 1. So I'm going to say that the minimum allowed value is 1, and that the maximum allowed value is 92, because that's the biggest value I found. And obviously you're going to say, if you're paying attention at all, well, 92 is not a very sensible maximum for that, because, you know, it's true for this data, but there might be elements above 92. In fact, there are. And then separately from saying that it's in this range, it also, as a separate constraint, notes that they're all positive. And the reason it does that is you could take out the other two constraints and still leave the constraint that says it has to be positive, because that's a different thing, which doesn't make any difference when the minimum's 1, but if the minimum had been 5, that would be a different thing. And it might be more significant if suddenly they'd gone negative. It also puts in a constraint that says there mustn't be any nulls in it. The maximum number of nulls is 0 because there weren't any nulls in the data that we gave it. And similarly, there must be no duplicates because there were no duplicates in the atomic number in the data that we gave it. And in fact, there shouldn't be any duplicate elements. And then for string fields, it's slightly more involved. It puts the minimum and maximum length. And again, you might say there probably isn't an intrinsic reason why the name shouldn't be fewer than 3 characters and shouldn't be more than 12 characters. The more interesting thing that it's done is it's generated a regular expression that, for those of you who speak regular expression, says that all the names seem to be a capital letter followed by some number of lowercase letters. And that's quite useful. And so on. So that's the constraints it's generated. And the recommended process, which we'll sort of follow, is to go through and say, yeah, I don't like that 92. Let's either take that out or let's set it to 150 or, you know, whatever we think is a more sensible value. Now, what should be true with TDDA in most cases is that the training data should obey the constraints that were generated. And so we can check that by using the TDDA discover, no, the TDDA verify command. So we can say TDDA verify, and then we tell it what data we want it to verify, which is the same data that we discovered on in this case, just to check that it's working properly. And we also give it the constraints that it's supposed to use, elements 92.tdda, and it will go through and verify them. And it turns out there were 78 constraints, and they all passed, which is exactly what, none of them failed, which is exactly what should have happened. So that's good. Okay. So the next stage is supposed to be that we now, well, the next stage is really supposed to be that we look at those constraints and we edit them by hand and make them more sensible, taking out, loosening constraints that are too tight, or removing constraints that are too tight, and possibly adding constraints that it hasn't put in that we'd like to be in there. But the other thing we can do is we can verify new data with this and see what passes and fails. And what I've got, as well as the data, it's still 10-year-old data, but as well as the 92 elements, I've got the rest of the periodic table as it was when I downloaded it from Wikipedia a long time ago. And if we look at that, in fact, maybe the easier thing is to look at that in here. Elements 118.csv. That data has elements that didn't even have a name at that time, like Ananoctium and stuff like that, as well as all the same stuff at the top, exactly the same data at the top. Okay, so what we could do, and this is a slightly artificial example, but hopefully you get the idea, is we could try verifying that larger data set with the constraints and see what happens. So we'll run the same command, but we'll put in 118, and not everything passes. And we kind of knew not everything would pass because the maximum allowed atomic number was 92, and all of the new data has atomic numbers higher than 92, so all the new records fail. But in fact, 17 constraints failed. And this view just gives us a kind of overview. So we can see there are ticks and crosses, which I'll probably make red and green soon, or red and blue, or whatever you want for colorblindness. But anyway, we see the max on Z failed, which is exactly what we expect. That's the 92 thing. We see that the name maximum length failed, again, unsurprising, and so on and so forth as we work down. So that's just given us the overview. Not everything's good, some stuff failed. So either we've got bad data or we've got constraints that are too tight in this case. So let's have a look at that. So as well as the verify command, there's a detect command. And the detect command not only checks the data, but writes out whatever information we want about the bads. And so you tell it where to write it. I'm going to write it to bads.csv. And there are a few flags that it will help to put in. We're going to say minus minus per constraint, which says don't just tell me whether a record failed, but tell me the individual columns that failed. We're going to say minus minus output fields, which says write all the fields out, not just the ones that failed. And we're going to say interleave, which says put the columns that tell you whether a field failed right next to the original column, so they're sort of interleaved rather than all at the end, which is what it does otherwise. And possibly is the wrong default. So I'm going to use this command, and I'm going to add minus minus per whatever it was, per constraint. And I'm going to say minus minus interleave, and I'm going to say minus minus. God, it's very hard working on a small screen like this, isn't it? Output fields, yes, output fields. So if I got that right, we've now got a bads.csv, which has got the stuff in it, but again, that's hard to read. So if we do that in something where we can read it, and we see that, indeed, everything after 92 failed, 27 records failing, 118 minus 92 is 26, but also helium failed. So it's a bit odd that helium failed, because helium didn't fail before. So what's going on with that? Well, what's going on with that is you can see we've got these OK columns for things that had failures, and so we're looking for zeros in that OK column, falses, things that didn't work. And if we look across helium, we see that we've got a field for the melting point in degrees C and, a bit redundantly, the melting point in degrees K. And we see that it's got nulls in it, but the constraint said that, well, the constraint looks like it said we weren't allowed to have nulls. So let's look at what's going on there. And what it's actually done is, what field was that? That was melting point. What's actually happened is that, as a special case, when you give it data with a single null, it accepts that and puts a maximum of 1 in. The reason it does that, if you're aggregating things that have nulls in them, you usually get one row and exactly one row that has a null in. And so it treats that as a special case and writes 1. And there was only one row in this original data, not because it was an aggregate, but just because helium's the only one we don't have a melting point for. And therefore, it put in a constraint that said we can only have one, and there was only one, so helium was fine. But now there are lots of null melting points, so that's no good. So the idea is that we go through and we examine everything like this, and we say, well, let's take that constraint out. And the slightly painful thing is JSON is quite hard for humans to edit, or at least it's quite hard for this human to edit. But I'm going to take that out. And then, what else has failed? Well, let's just look at what fields have zeros in. So I'm going to count the zeros in all the OK fields, and we see we've got 26 in atomic number. Well, that's not a surprise at all. We've talked about why that's obviously silly. So we'll take out or increase the constraint on the atomic number. We saw that this length was no good as well. So again, I think I'll just take that out. We've got 7 in the symbol max length. So we've got a problem with symbol max length because they were only 2-digit symbols up to uranium, but we have 3-digit ones like UUO for ununoctium as it was. And in fact, our regular expression also says we can only have 2 symbols, so we'd better increase that to 3. And this is a bit tedious, but I will do it because I'd quite like to show you it. The atomic weight has a maximum that's no good. Well, again, that's not, if you know anything about chemistry at all, or physics, you know that the atomic weight, the atomic weight tends to go up as you go down the periodic table. So we'll take that maximum out, and we've actually got 2 copies of that for some reason as well, relative atomic mass as well. So we'll take that out, and the atomic weight is occasionally null 1. We didn't want that, but that's okay here. So actually we could set that maximum to 1. And the etymology, well, what are the etymologies like? If we look at the etymologies are just free text. We shouldn't have regular expressions on those at all, and we shouldn't have a maximum length. So we'll take the various regular expressions it's generated out, which weren't very good anyway, and we'll take the maximum length out, and let's repeat our thing. And what else? So relative atomic mass, null. Oh, and we'll have that in atomic weight, because this is annoying data. Oh no, we've done that. Yeah, we'll set that to 1. And melting point in Kelvin is often null. I think we've probably taken that out already. In boiling point and density. So I know this is slightly tedious, but we'll get there. It's a lot less tedious than writing these constraints by hand. So we wanted to take out the nulls constraint there, I think, and we wanted to take out the nulls constraint there. And for density, we want to take out the maximum and allow it to be null, because we don't know what what the density of ununoctium is. So what we'll now find, if we run it again, is that I am not any good at editing JSON, I suspect. God, we didn't. We got it down to 1 record failing. Brilliant. Let's see what our record that we didn't fix was. Let's look at it. It is ununceptium. And what was our failure? The etymology. The etymology was null for ununceptium. So if we fix that, right, so we'll set that to 1, and then hopefully everything will pass. So there you go. So that's pretty much what I want you to do. And I know it was a bit tedious watching me do all that, but compared to actually doing it by hand, that was really pretty good, I contend. Okay, so let's go back. So one thing I should say is CSV files. CSV files. Everyone hates CSV files. Everyone knows that CSV files are problematical. They're very difficult to round trip. They don't contain enough metadata. They're incredibly unreliable. But of course, there are all sorts of reasons why we use them as well, like all the Unix tools and the fact we can edit them and the fact that everything can read and write. Okay, they might not read and write them the same way, but at least they read and write them. So I don't want to rag on CSV files, but if we ever have a choice not to use CSV files, we should probably do that. The TDA library supports Parquet files as well, and the same data is available in Parquet, and if we use the Parquet versions of the data sets, then everything just works exactly the same. You can do that for inputs and outputs, and the same constraints should pass because the CSV files are written in such a way that this CSV reader reads them correctly in the same way as the Parquet files. So that's a good thing to do if you can, but if you can't, you know, you can't.
I have a question. What platform was that, the platform that had the white background where you would run the tables and then it comes out with colored formatting? Because that wasn't your terminal.
Ah, that's the commercial software mirror that my company produces. Yes, it's very nice. You might anyway. But this isn't a sales pitch for that. It has a fancier version of all this stuff as well. But yeah. So okay, I think we've done all this, haven't we? I think we've done all this. We've done all this. We've done all this. So yes, the recommended procedure is you run discovery. You on ideally known good data or believed good data or fairly clean data. You then adapt the constraints by hand. You then validate it maybe against a holdout set or something like that, or the first production data that you've got. And then you use it, and you run verification, and you monitor it, and you continue refining the constraints. Why do you continue refining the constraints? Well, there's an important thing here. So many of you will know Sherlock Holmes and perhaps have read Silver Blaze, or perhaps have read Mark Haddon's fantastic book, The Curious Incident of the Dog in the Nighttime. If you aren't familiar with it, Inspector Gregory from Scotland Yard says, "Is there any other point to which you would wish to draw my attention?" And Holmes says, "To the curious incident of the dog in the nighttime." And Gregory says, "The dog did nothing in the nighttime." And Holmes said, "That was the curious incident." And of course, what had happened was that the person whoever got murdered, didn't cause the dog to bark, which meant it wasn't a stranger who'd come in off the street. It was someone already known to the dog. Why is this relevant? If you don't work with clean data and you don't verify the constraints, then what will happen is you will miss out constraints that ought to get generated, and they will allow bad data through, and you'll only find it downstream when someone comes and says, "I thought you were checking this data. Why have I got lots of null customer IDs and 500 million-year-old customers," and you know, all that sort of stuff. So it's a much better idea not to do that. And the commercial version can accept bad data rather than good data and doesn't necessarily generate tight constraints. But we're not here to sell that. So the ideal process is exactly the one I just went through. When you run it, you'll get false negatives. And by a false negative, I mean stuff that should have been flagged, should have been detected as bad, but wasn't. And what you have to do then is you have to add in constraints or tighten constraints. And you'll get a lot of those if you trained on bad data. But what you'll also get is false positives, which is what we saw here, all sorts of stuff that was flagged because our data was not sufficiently representative or you know, didn't cover the full range, or because it was collected at a point in time and you say, so the maximum customer number's this or the maximum date's this or whatever, and those things go up and they're not sensible to have as constraints like that. So that's that. The reduced process is you discover on training data without bother checking it, you don't bother to verify the constraints, you throw it into production, and then what you'll get is a whole lot more false negatives than in the other case, and also obviously some false positives. That's just another repetition of the same stuff, but with different data, which is also supplied, so you can play with this, some banking type data with transactions and customers and things. Okay, how am I doing? 10 past 4, 40 minutes. How long was I supposed to be? 20 minutes. And that's okay. I think we can talk about RexPy. So RexPy is the second machine. This is the one for figuring out regular expressions from examples. So most of you will know regular expressions. Some of you may not. They're ways of characterizing textual data, string data. So if we have this phone number here, the most specific regular expression that it matches is the one that starts with an up arrow, which means this is the start of a string, and then it goes 212-977-0031. And then dollar means that's the end of the string, so that terminates it. The only string that matches that is the one there. The reason we've got backslashes in is that dashes are special characters in regular expressions. It probably doesn't matter in this expression, but in general, people tend to escape minuses. So that's the most specific characterization of that string as a regular expression. The least specific one is the one at the end, which is up arrow dot star dollar, which many of you will know means start the string, have dot is any character, star means 0 or more of them. So start the string, have 0 or more of any character, and then finish the string. Well, that obviously matches any string. So that one's too general to be useful, and the first one's too specific to be useful. So what we want is something between those two, and we have all sorts of things we could have in between. So the second one says, well, it's got 3 digits that are 1s or 2s, and then a dash, and then it's got 3 digits that are in the range 7 to 9, and then it's got 4 digits that are 0s, 1s, and 3s. That's a bit over-specific too, but it's not as specific as the first one. Or you could have \d, which is the same as the range 0 to 9. It's 3 digits followed by 3 digits followed by 4 digits. That's the one that we probably want. That's the one that any of us would write if we enjoy writing regular expressions. And then the slightly too general one is one that says, well, it's a bunch of digits followed by 1 or more. So plus is like star, except it means 1 or more. It's a bunch of digits followed by a dash, bunch of digits followed by a dash, bunch of digits, and it ends. So those are regular expressions. Here's a regular expression for a postcode. I'm not going to go through it. Now, as Jamie Zawinski said, some people, when confronted with a problem, think, I know, I'll use regular expressions. Now they have 2 problems. This was his signature for years on comp.emacs.xemacs, for those of you who remember 1997. So the pros of regular expressions is that they're very powerful, they're very widely supported, they're very fast. And the disadvantages of regular expressions, the cons, are that they're ugly, sometimes very ugly. They're hard to write. They're harder to read than they are to write. They're even harder to debug. And they're pretty bloody difficult to quote and escape, though if you're working in Python, raw strings are your friend, because raw strings at least mean that the backslashes don't get treated as special characters, and regular expressions tend to be full of backslashes. So what we thought was, why not let the computer do the work? So with RexPy, which comes, it's another tool that you just have with the thing, you can give it a bunch of strings, so like here are some phone numbers, you can say RexPy and you can feed them in, or you can pipe them in, or you can give it a file of them, or you can give it a data frame of them, or whatever you like. And it will come up with one or quite often more than one regular expression. It quite often takes, I should probably have typed RexPy first, shouldn't I? It quite often takes more than one regular expression for this stupid library to work. So this generates 2 regular expressions because it doesn't like combining spaces and punctuation characters, but whatever. So that's usually a good start, and that can be quite helpful. And you just get that if you work with the TDDA library. And that's just the help, and that's how you can use it in a program, and that's how you can use it with pandas, and blah, 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 blah. Now, the crucial thing to understand about it is if you throw free text data into this, it's just going to grind its gears for hours and produce absolutely nothing useful, because there is no sensible regular expression for free text. What it's for is the sort of things you'd actually write regular expressions for, like UUIDs and zip codes and postcodes and credit card numbers, and things that have got structure that you can see, but just it's a little bit hard to figure out how to turn that into a regular expression. And that's why we have the -r flag. If you feed novels in, it's not going to make your day better. Okay, it's almost impossible to believe, but we're 1 minute ahead. Is there 1 minute's worth of questions, or should we just press on? We'll probably get behind later, so. Yeah.
I have one related to the verification. Whether there's any way to attach that functionality into a streaming setting.
Okay, that's a very good question. So the question was, I've kind of shown batch verification. What if you've got data streaming through? I have done that. The current library doesn't do that, but I probably will add that in. It wouldn't be very hard to to generate a Python function or whatever that would do it. And what we did before was fed that into one of the things beginning with K that I can't remember the name of that would collect them. Some kinds of constraints are more difficult with that, like checking uniqueness and checking for duplicates and maximum number of nulls and things like that are obviously a bit of a problem. You have to have windows and reset them and stuff like that. But for the simple ones that are row-based, that's completely feasible, but it's not part of the library at the moment. And it's not even part of the fancy commercial one we're not going to talk about in this session. But I may well do that, because it's a very obvious thing. Yeah, good question. There's way more than a minute's worth. Well, I'll take one more. You've got a very red T-shirt on, ready orange T-shirt on.
Some other packages out there to do data validation, like Great Expectation,
Yep.
Pedantic, et cetera, et cetera.
Yep.
I guess, how is TDDA different from those?
So Great Expectations I'm fairly familiar with, and it's great. The thing that I would say about Great Expectations is that it has much less emphasis on machine discovery. It's much more about writing constraints. And it's about writing more and more different kinds of constraints, which to my mind is completely crazy, because something I haven't talked about is actually the basic kinds of constraints that TDDA works with, I think are adequate for almost all the validation you want to do, provided that you're willing to derive new fields, if you want to, and produce aggregate data sets that measure things on a per store basis or a per country basis or whatever, and check those separately. you also talked about Pydantic. Pydantic isn't really for data frames, it's really for Python data structures. And if you're working at scale, that's just no good. And besides it's all based on this ridiculous concept of types in Python, or rather type hints in Python, which in my view are one of the biggest dead ends that Python's ever gone down and should just be resisted, because it's a dynamic language, people. You don't want to be writing it and saying, let's make it so it can only do very, very limited things. You want, the whole point, if you want type hinting, you should be using a real typed language like Rust or something like that will check types for you, not one that will just allow you to litter your code up with types that aren't even checked. It's like really hate. Anyway, sorry, I'll stop ranting. But thank you for the question. Okay, so testing data pipelines. Well, what's the difference between testing data pipelines and testing any other sorts of software? Well, first thing is if you take the real TDD dogma, which a lot of people don't, but if you do take it that you're supposed to write the tests first, that can be very difficult with complex data analysis, because often you don't have any way to generate the data that you want until you've written the program, because there's nothing else that generates it. Now, that's not a huge deal, but the TDA library helps you to generate reference results that you want to test against directly from your code and manage that in an efficient way. Very small deal. The much bigger thing is that the artifacts that we want to test in data analysis are often not completely fixed. Now, whenever I say that, the first two things that people always think about are random numbers and precision. And those are not the two main things I'm talking about. Random numbers you can usually fix with seeds, certainly if you're running in serial. And actually, even floating point things should come out exactly the same if you perform the same sequence of operations in the same order, certainly on the same platform, but even across platforms, because everything uses IEEE. So it's not, those are factors, but they're not the main factors that I'm worried about. What I'm mostly worried about is things like you produce a graph, and it's the same graph. When you put it on the screen, it's the same. It produces the same pixels. But if you look at the file is not the same. So I sometimes talk about that as they're semantically equivalent. They're equivalent files. They mean the same thing. But as files on disk, they're not the same thing, or as data structures in memory, they're not the same. The sorts of reasons they're not the same are because they embed version numbers, they embed host names and dates, they have random labels in them, which you can't control because it's not your seed, it's Matplotlib's seed or whatever. They are dictionaries that are naturally unsorted, but they get deserialized in different orders, and so you know, all this kind of stuff. So there are lots of reasons why you might want to check two objects, two outputs that, and what you want to check is that they're equivalent, but not necessarily identical. Some parts of them are equivalent. And what the TDA library does is provides lots of new kinds of assertions that help you to do that by saying things like, check these two text things are the same, but ignore lines that look like this, or lines that contain these regular expressions, or the bits within the regular expressions, or apply these pre-assert normalization functions before you do it. And there are things for comparing data frames and saying, well, compare these data frames, but ignore this column, and don't worry too much if the types are a bit different, as long as, you know, if it's a 32-bit versus a 64-bit float, well, that's fine as long as the numbers are the same to 6 decimal places or whatever. Okay, so there's that. There's also, this is kind of true for all software, but there's this whole idea that you should write a separate test for every single case, and usually I hate doing that. Normally I like writing loops that have a whole load of inputs and a whole load of outputs, and you check them all because that's much more efficient. But the problem is what you don't want is when one fails, you don't see, the other tests don't run because you've raised the error. So the TDA library has quite a lot of multi-assertions where you can say, check that these things are like these things, check them all, and then at the end of them tell me which ones failed. They can be slow to run. All test libraries have, well, I think all test libraries have ways of running a subset, but TDA has a much easier way of just running a subset, so when you're working on a single function or a few functions, you can run just those. There's a real problem that often you generate output in memory, and then when it fails, your test, well, you've come out of the program, so you haven't got it in memory anymore, so you can't examine it. So TDA has some nice functions for writing outputs to disk and telling you what diff function you need to use and being able to compare them and stuff like that. And it has ways, another common problem is that if you make a systematic change to something that affects a whole load of tests, like you're writing stuff out using a template and you change the template and you had 500 tests that use that template, now you've got 500 results that have changed. And so TDA makes it easy safely to rewrite reference results once you've convinced yourself that the new result is in fact correct. That can also just be because you got the test wrong and now you realize that. that the code's better than your test. So, general setup. My contention is that even the least diligent data analyst always develops analysis processes in the context of data and always does some level of checking of them. So, you know, you take your input data, you work on developing your process, and then you everyone at least checks that it's not obviously wrong. Right? So the idea is, well, if you do that much, what you should do is you should capture your inputs, you should capture your process, capture as in record your inputs, ideally capture your analytical process as a script that you can just run, and if you can't, at least have it as a checklist that you can work through. Capture your outputs representing what you believed were good enough or probably correct results, and have some kind of a diff procedure, a verification procedure that you can check that the code still produces the outputs that you said were okay if you feed the same inputs in. And that's useful if you change the code, but it's also useful if you don't change the code, because it turns out, even though it seems counterintuitive, there are thousands of reasons why code rusts, as we call it, which means that it used to run fine and now it doesn't, even though ostensibly nothing changed. And there's a blog post actually called Why Code Rusts on the TDDA blog that talks about that if you're interested. Okay, so let's talk in detail. Reference test support. Actually, I think I've told you this. So, you know, you can compare an actual string in memory or file to a reference string. You can exclude lines that contain particular substrings, or the bits of lines that contain that match regular expressions. You can pre-process both of them beforehand. You can write the actual string produced when a test fails to file. You can, it'll tell you what diff command you need to use to look at them, which also turns out to be the same command that you need to use typically to copy it to be the right reference result if you want to, though it can do that for you. It's obviously not the same command, but it's essentially the same command. You can check multiple files in one go, and it can rewrite reference results for you. So there are three main kinds of assertions. There's assert string correct. There are these for PyTest and unit test. This is the unit test version. Assert string correct, where you give it the string and the reference path, and whatever parameters you want to say, like, you know, but don't worry about these regular expressions or whatever. Assert that a file's correct. So if you've written a file out to disk and you've got a reference file, it will work with that for you. And the multiple files thing, check this set of files against this set of files, and then tell me at the end of it what's going on. So we'll look at an example. So I've got in the code in another one of the examples directories, code for generating two web pages, these two web pages here, one of which gets generated in memory and one of which gets generated in a file. So we're going to look at that. So if you are following along, next to where you are, there should be reference tests. And I'll show you the two web pages that get generated. Actually, it's in reference, not test data for some reason here. And we've got the string result, and we've also got the file result. Okay, so there's that's the file result, and that's the string result. So, tests. Yeah, we've got tests here. We've got tests for both unit test and PyTest. I'll use the unit test ones because it's in the standard library and it doesn't get enough love. So these tests, if we run them, so this is what testing usually looks like. You get a dot when a test passes, you get an E when you get an error that's sometimes red, and you get an F when you get a failure. So an error is when there's like a bug, and a failure is like when the test assertion fails. So these all pass, and we've got two of the, if we look at this code, then at the end we've got a class called test unstructured data example, which has got two test examples, string generation that calls this generate string function and then calls assert string correct, the actual string that got generated together with the result in a file, or rather the name of the file that we're testing, and these ignore substrings, which says ignore lines that have got copyright or version in them when you're doing the comparison. We've got another one that's basically the same but for the file example, except it writes the result to file there rather than just generating it in memory. And again, it ignores the copyright and version lines. So that's what that is. And then there are some data frame tests above that we'll look at in a minute. So if we if we look at generators, which is the thing that generates the web page, there's this generate string function, and there's this generate file function. And what we're going to do is we're going to edit both of those so that our reference results are no longer the same as what's actually generated. So I'm going to search for terribly, which is on the web page, and change it to very. And I'm going to search, very with 2 Y's. That's even better, isn't it? And we've got these colored letters in TDDA. So if I set one of those is C0, so instead of C0 8080, I'm going to have 8080 C0, which is some different color. So if I run the tests again, 2 of them fail. So we still ran 7 tests, but we got 2 failures. And what I want you to do is, this, I'm sure this isn't true of people in this room, but a lot of people get really freaked out when they see a whole load of output like this and just think that's really scary, it's failed. Just like they say with Rust, the Rust compiler errors, if you read the error messages, it will tell you what's going on. And the failures here, it's telling us, so this second one's the string generation, and it's telling us that one line was different, starting at line 31, and that I can compare the raw thing that was generated with the expected result using this diff command. So let's do that. Now this is just using diff, and what we see is that actually there are 3 sets of changes. The copyright line and the version line are different, but that's not what caused the test to fail. We saw that before because we told it not to worry about that. What's different is exactly the stuff that we knew ought to be different, which is it's not very exciting, and don't worry about the new line, that's just it. That's not interesting. So that's good. And if we look at the other one, the file result, it's kind of, well, actually, before we look at the other one, it also says we can, so if we do open diff, which might make you happier, actually, might make all of us happier, this is like the visual diff of it. And what you see is, I mean, it's probably too small for you to see, but at the bottom is the difference, that grey line with 2, this one here. This is terribly, and this is very. But you also see at the top, there are the copyright and version lines, and what it's done is it's rewritten both files. Sorry, it hasn't, no, it's showing you the differences, it's showing you the differences. But if you look at the second diff command, and run that with opendiff, or indeed with diff, so if you run it with diff, then it only shows you it's not very exciting and it's not terribly exciting. And if we look at opendiff, we'll see how it's performed that amazing feat. And the way it's performed it is it's rewritten the copyright and version lines in both of them to contain both of their outputs in the same form so that now those don't show up in diffs. Okay, so that's useful. So if this is what we want, then what we can now do is take that first diff command that we were using, which I think is that, I'll copy it again to make sure I'm copying the right one. We want this to be the raw one. We could take exactly what it used there and just turn that into a CP command. So if I've verified that this really is now the correct result, then I can copy that, and now that test will start to pass because we've rewritten the reference result. Now, the obvious health warning is if you just get into the habit of whenever a test fails, you just update the reference result, that's not going to end well. That's not what the data scientist who's taken the Hippocratic Oath does. What the data scientist who's taken the Hippocratic Oath does is you look and make sure that the new result really is the correct result, and then you update it. If we look at the other one, it's basically the same. It's not very interesting. Actually, we could look at the results that got generated, couldn't we? So if instead of open diffing them, we open them, at least on a Mac, I'm not sure how this works on other machines, then we'll see that that's the one with very in it, and that's the one with very in it. That's probably doesn't matter anyway. You can open them as well. So the other thing about this is I was talking about. So there is also capability in the library to rewrite the test results automatically for failing tests. So if you run the tests with either -write all or -W, with unit test anyway, then instead of running the test, well, it will run the tests, but it won't do the checks. It will just write out the reference results, the actual results as reference results. And doing that over the whole file is generally a terrible idea because then you're updating all your tests and you don't want to do that. But if you only want to update a particular set of tests, what you can do, or if you just want to run a subset of the tests, what you can do is you can go in and so you can import tag from the TDDA library, that thing here, and then you can use that as a decorator on either individual tests or on test classes, So here I will tag this class, which has got the two tests that we want in. And then if you run saying -1 or minus tagged, oh, well, that's not going to be very good, is it? If you run this with -1, then it will only run the tag tests, which is that class. We only get one failure now because we've already updated one of the reference results. And if we add -w, or just -1w, in fact, we'll do it, then it rewrites our reference results. So I've a second time updated the reference results. And now, if I run, obviously, the tag tests, everything passes. And indeed, if I run the non-tag tests, everything now passes. So that's a practical workflow that gives you an amazing amount of power to shoot yourself in the foot, but also the power to be quite productive if you elect not to shoot yourself in the foot. 4:30, that's not bad. God. Am I gabbling? Am I going much too fast? You see, you're all too polite to say yes. Okay, so that was that, we've done all that, we've done all that, we've done all that, we've done all that. Okay, so let's talk about data frames. Let's talk about checking structured data. So again, there are a whole load of assertion methods for comparing a generated data frame to another data frame, or to a Parquet file, or to a CSV file. It'll again show you the diff command to look at differences. The diff's a bit less useful for data frames, but you know. You can check multiple CSV or Parquet files at the same time. You can choose a subset of columns. You can tell it whether to check the types. You can tell it whether it care about column order. You can tell it to ignore the data in particular columns. You can choose precision for floating point comparisons, as you always can with these things. And again, it supports automatic rewriting of verified results if you want it to. So, oh, that's I've just gone to the wrong place. God. Okay, so yeah, reference data frames. So we've got these reference data frames. They're a little bit hard to look at, but if you run show.py, which is this two-line thing here, this is the sort of data that our data frame generator and dataframes.py generates. So it's just an incredibly simple, tiny data frame that's got an integer column that just counts up, and some reals and some random numbers, which are random, so they change each time, and some booleans, and the square of I and R square, the square of R. I thought that would get a laugh, but there you go. And then S, which is just a string field that uses 3 decimal places the R square value. So that's what it generates. It generates it using this, you're going to be impressed with this incredibly sophisticated function here that does that. Obviously not a good way to generate a data frame, but okay for a trivial example like this. Obviously you want to use vector, well, I suppose these are vector operations, but still not really a good way to generate a data frame. Anyway, what are we doing? So we've already got tests running that test these things. Oh yeah, we should look at the tests. So we've got these tests. So I'm going to remove this tag because we don't want that tag anymore. And so we've got 5 different functions, one of which tests the data frame saying check all the fields except the random field. That's what that columns thing does. And it's saying just check those columns and check the types of those columns, but that's all. We've also got one that checks a CSV file against a reference CSV file, again ignoring the random field. We've got one that does it with Parquet files. We've got one that does it with multiple CSV files. We've got one that does it with multiple Parquet files. And they share reference results, but it's just showing the different kinds of functions that are available. So what we're going to do is we're going to change the generator in a very simple way. We're just going to say when you construct that string, write it to 2 decimal places instead of 3 decimal places. And so it's not on the screen anymore, is it? But so this is what we had before, and if we run it again now, having changed it, you see we only get 2 decimal places on this string, right? So obviously our reference result's different, and the tests are going to fail. And what I'll actually do is I'll tag this class. You could tag individual tests instead, but I'm going to tag this class. And okay, and now if we run the tests, we get 5 failures. We get 5 failures because all 5 tests use that function which generated this S column, which is different. And so again, we get a similar kind of thing. We get quite a nice summary of what's wrong. So if we look at the last test, which is the Parquet one, it tells us, well, not very helpfully, false is not true. I mean, it's true that false is not true, but it's, you know. But it gives us a different summary. So the data frames have different structure. Sorry, the same structure, same columns, the same shape, in fact, but different values. In particular, 8 of the 60 values are different. The number of rows with differences is 8 of our 10 in this case. And the number of columns with differences is 1, and it's the column S. So that's a pretty good start. It gives us a diff command, but that diff command's not actually all that helpful because, well, I mean, I'll run it, but I'm sure you all know what that's going to do. Oh, look, the binary files differ. But what I'm working on, and it's very embryonic, you're welcome to use it, but it's definitely not finished yet, is TDDA diff. And what TDDA diff does is shows you visually the difference between 2 data frames. Now, it's including the random numbers because I haven't yet given it anything to say, ignore these columns, and we didn't tell it to ignore these columns. We just did a diff on the whole data frames. But here, the red ones are the ones we actually generated, and the green ones, or the first example in every case if anyone's colorblind, and the second example in every case. The first one's the actual, the left, whatever you want to call it, and the second one's the expected. So having confirmed that this is exactly what we wanted, because we deliberately changed it to be 2 decimal places rather than 3 decimal places, what we could now do is, again, run our tests. I should really go down to a smaller number and check all the other ones, but I know in this case, and we don't have much time, that everything's fine. So if I run that with -w, again, that will update our results. And now, oh, but I did the bad thing. I didn't use -1, so I updated the string results again as well, which was really bad, naughty me. But it's okay, we've got version control, so we'd go back and, you know. Yes. So I should have done that. And now if we run, well, just the tag tests or all the tests, everything passes. And that's wonderful. So there you go. So that's reference testing by hand, and that's trying. I can't believe it. We're actually on time. I really must be gambling. So let's talk about automatic test generation. So I talked about the high-level concept of reference testing, which is your analytical process. You develop it with some data, and what you should do is you should record the inputs, and you should record the script, or the process as a script ideally, if not as a list of numbered steps. It does have to be a script for GenTest. And those are things you still have to do. But what GenTest will do for you is it will record the reference outputs for you, and it will create the diff procedure for you to tell you whether it's working, and it will write the tests for you. So the idea is you feed in some command, some command line command, like sh, classify.sh or whatever. GenTest goes away, writes you a Python script that tests that script, whatever it is, that thing that you can start from the command line, and it records reference results in a directory under ref, and it tests it for you. Sounds pretty good, right? Sounds pretty good, right? I mean, we can just stop if you like. So next to the reference test examples, we've got GenTest examples. There's actually an example in here too that you can work through that shows running R to do a whole load of stuff to generate a quarto output and see what's going on with that. But we're just going to use example 2.sh, which is this script here. So it's just a script that says, hey cats, this is GenTest running on escher.local, which is the name of my machine. At some point when I did this, I was in Munich. I have to say the weather was better in Munich, though the weather's not bad here, and it wasn't necessarily better in Edinburgh. Today, Friday the 14th of June, 2024, blah, 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 blah. It's proper Greek here. Teach some Scottish. And then it writes a random number to file 1. And if we look at file 1, which it's written, it says, let's have a file as well. Here's a number, 24,970. So typical little script that doesn't, well, not a very typical script. But, and the script, you can obviously look at it. It's exactly as complicated as you'd think. It's just a whole bunch of echo statements that do all those things. So GenTest has a wizard. Let's use the wizard and see what happens. So you just say TDDA GenTest. This is the artificial intelligence bit of the talk for those of you who are... So it says, enter the shell script to be tested. Well, the shell script that I want to test, it doesn't have to be a script. It's just something you can execute at the shell. But this one's going to be example 2.sh. OK, enter a name for the script. Well, the general rule, of course, is, as with most wizards, you can probably just accept the defaults and it'll be fine. So yeah, call it that. Do I want to check all the files it writes under the current directory? Yes, I do. Do I want to check all the files written in the temp directory? Yes, I do. Are there any other directories that I think it's going to write files that we probably ought to be checking because I don't really want it to check the whole file system? So there aren't in this case. Do I care about what it prints on stodout to the terminal? Yes, I definitely do. Do I care what it writes to stder? Yes, I do. Would I like the exit code to be 0? I'm sure most of you know that the convention in Unix is that correctly functioning scripts scripts without errors return 0, and scripts with errors return numbers between 1 and 127, indicating the error. And so we would like that. Is it okay to clobber previous outputs if they exist? Yes, it is. How many times to run the script? Now, that's an interesting thing. It defaults to 2, and that's what we're going to do. And that's it. So it has run that script twice. I mean, it's pretty fast, isn't it? And it's generated test shirt example 2.py. So let's have a look at that. And what it does is it has some boilerplate stuff, and it has a fixture at the start that actually runs our command. And then it writes tests that say check that there's no exception. So check that like an actual exception wasn't raised while we were running it, because that's usually bad. Check that the exit code was 0, because that's what the exit code was when we ran it. Check what came out on stodout. Now that's interesting. So it's written into this reference subdirectory a file called stodout, and it's recorded in it what got produced by the script, but it's told it to ignore the substrings. What substrings is it ignoring? It's ignoring one that's got my path in it, because that might be a bit specific to my machine. It's saying ignore that date, probably because that wasn't the same when we ran it twice, or maybe just because it knows it's a date and it shouldn't do that. And ignore the host name because it knows what the host name is, and when it sees the host name, it reckons that might be a bit specific to this host. Check stder, which was actually empty, and check what's in file 1 that gets generated. And we've been sort of lucky and sort of unlucky that it's generated a regular expression to ignore, and it said it should be a digit, it should contain a number that's got 4 or 5 digits. We're quite lucky it said 4 or 5, because usually it just says 5, because usually it generates 5-digit numbers, but occasionally it generates 4-digit numbers, or 3-digit numbers, or 2-digit numbers, or 1-digit numbers. And so because it's 5, this is going to be pretty successful. So if we run this test, what's it called? It's called that. Then it will almost certainly pass. We can run it quite a few times and it will pass. If we run it enough times, it will start failing. So let's try running it 50 times. Oh, let's try running it 50. That's the wrong thing to. Oh no, it's not. I need to say Python, don't I? Let's run it 50 times. And if we're lucky or unlucky, depending on how you look at it, we'll get a failure, and maybe we won't. But the reason we'll get a failure is because eventually it'll generate a 1 or a 2 or a 3-digit number, which won't match the regular expression, so it will fail. And then because I'm just running it in a loop, there you are, it failed there. And the reason it failed is because it generated a shorter number. But so, it's not perfect. The tests don't always work. It's, health warning, artificial intelligence, but it's, it's an interesting start. It's not exactly a toy. I mean, it really does work, and it can give you a very good start, but it's definitely not. I am not saying you don't need to bother writing your own test. Just pass it through gen test, and everything will be fine. But it's quite good, particularly for this case where really all the testing you have done is check that you got one sensible set of outputs, and you just want to kind of codify that. Okay, so quarter to 5. I can't believe this. We're gonna get through it all. Oh yeah, so how does it do it? We've probably kind of seen how it does it. It looks at stodout, it runs it multiple times, you can tell it to run it more times. It looks at what's different in the output each time, and it uses rexpy to generate expressions that say, well, don't look at the bits that vary, only look at the bits that don't vary. It looks at the exit code, it looks at stder and does the same. It looks at what changes in the file system. It looks at your environment, so it knows the directory you're running in, it knows the date, it knows the host that you're running on, and so it looks for those strings and says not to focus too much on those. And it looks for the differences between runs, and it makes intelligent decisions about how and what to test. And it's largely enabled by rexpy. Oh yes, and this is artificial intelligence, none of your LLM crap. Okay, you've seen all that, 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 you've seen all that. Okay, errors of interpretation, or type 6 errors. Final part. So errors of interpretation are a bit harder. My view is that as whatever we call ourselves, data scientists, data professionals, data engineers, data whatevers, data analysts, It's not good enough for us to chuck some output and say, well, it's not my problem if you don't understand it. We need to work quite hard to try and make sure that people do understand it. Hippocratic Oath and all that. So some of you will have heard of the Mars Climate Orbiter, which I think back when $350 million was quite a lot of money, crashed at a cost of $350 million. And the reason it crashed was because it was a collaboration between NASA and Lockheed Martin, and NASA being a sensible organization worked in SI units, and Lockheed Martin being an American organization worked in imperial units, force pound seconds, and they didn't put units on them, so they tried to compare an FPS number with a metric number, and boom, the thing crashed. You're shaking your head. Is that wrong, Juan? Is that not what happened? Yeah. And that's bad, isn't it? They weren't pleased at all. So put units on things, that's one thing, but be aware that there are a lot more units and a lot more abbreviations than there are symbols, so be careful to make sure you communicate what kind of unit you're putting on it, and don't let people mix up meters and miles and millis and millions and millions and all those kinds of things. I talked about this earlier. Which class are we predicting? There's a really big difference between a 99.9983 chance of crashing and a 99.9983 chance of having a safe flight. It's really quite a good idea to say which is which. One of the good practices you see in a lot of things these days is for them simply to say more is better, or higher is better, or whatever, which is like stupid but really important. Regression to the mean. God, why did I put this in? Regression to the mean is more a formulation problem. A thing that I see people getting wrong all the time is not being aware of regression to the mean. I know everyone here knows regression to the mean, but I'm going to say it anyway. Regression to the mean is a phenomenon whereby if you take a population and you measure some behavior, and then you segment on that behavior, so you say these people spend a lot, these people don't spend very much, and these people are in the middle, and then you measure those same people and those same segments later, what you will almost always find is that the people who spent more before spend less now, and the people who spent less before spend more now, and the people in the middle spend the same. And that's because of regression to the mean. And very roughly speaking, regression to the mean happens because when you segment people like that, you capture some people in their typical state. Some of them are high spenders, and some of them are low spenders, some of them are medium spenders, but some of them you catch in an atypical state. And if you catch someone with a high level of spend, at a supermarket, it might be because they were having an enormous bash that weekend and buying 500 quid's worth of booze, but the next weekend they won't do that. And if they were above average last time, they're much more likely to come down than they might go up, but on average they'll come down, and that's regression to the mean. So be very careful when you're segmenting on behaviors and then using that and looking at differences, because you get fooled. I've been fooled by that, and I know a lot of other people have been fooled. I don't want to turn this into a rant about clustering, but be very, 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 very careful if you ever use cluster analysis. And if you use it for non-spatial data, I think you might be fooling yourself. I've got a whole series of blog posts called Clustering Considered Harmful. You can probably guess what it says. What are the problems? The problems are it's unsupervised, so you're not asking it to do anything particular, you're just asking it to find clusters. Clusters don't really exist. They depend on the distance function you use. They're often unstable. All that people ever do with clusters is they give them names, and then the people who interpret them just look at the names, and the names don't really mean anything, and so you end up either describing the cluster center, which is the average family with 2.2 kids and half a dog and half a cat and whatever, or you call them Vindaloonies, and then all people ever know about them is, oh, they're probably really keen on curry if you've called them Vindaloonies, but that isn't really a good characterization of their behavior. And the biggest thing is they use non-commensurate variables. So non-commensurate variables are things that can't naturally be compared, but you force them to be compared by doing, the equivalent. You create a numeraire, you turn everything into money, and you say, we're building these two roads, and this road or this railway, and the roads will kill 100 times as many people as the railway. So how do we compare those? Oh, we'll say a human life's worth, £1 million, and then that'll be fine. We can compare them, but they're not the same thing as the cost of the road or whatever. So you have to be careful. Anyway, so I'll stop ranting about that, but go read it if you're interested, and be very careful when you're using clustering. Type 1 and type 2 errors. There is no one in the whole world who knows which is a type 1 error and which is a type 2 error and is confident and correct about that all the time. It is the stupidest name that has ever been invented. And of course, Randall Munroe, who some of you will know, realized that and produced this fantastic cartoon that extended the taxonomy to include type 6 errors, which are correct result, which you interpret wrong. Type 1 and type 2 errors, unbelievably, are examples of things guaranteed to generate type 6 errors. So don't use type 1 and 2 errors, and obviously this whole section's about type 6 errors. Type 111 errors are mistaking tally marks for Roman numerals. So at this point, I'm just going to leave you to contemplate that, and I'm going to ask you all to write down the date on the screen, like in an unambiguous form. Write it down, write it down, write down the date. We all know why this is wrong, and we all know if we lived through the millennium. I mean, okay, if you weren't born in 2000, maybe there's an excuse. But if you were, no one should ever use two-digit dates. Significant figures and spurious precision. I'm not going to go through all this, but oh yeah, so I wrote a book a long time ago, 1996, about sustainability, and my co-worker who actually knew something about sustainability, I just knew maths and complex systems and things, wanted to put this table in. We're talking about the world's water, with the fresh water and the salt water, and 20,000 cubic kilometers of fresh water in clouds and 9 million in continental water and how much in sea ice and all the rest of it. And then he wanted to put this total in of 1,339,000,000 and 20,000, and that's it. So what's wrong with that table? Why is that table nonsense? Sorry?
You don't know the century.
No, well, I mean, you don't, but that's not what that's... So my problem with this table is that if you look at every digit in this line, each digit came from exactly one of the lines above, right? So this says 1.3 billion cubic kilometers in the oceans, but it's not accurate to, the same level of precision as this number about the clouds. So it's absolute nonsense to add these up and put none of these digits after the 1.3 means anything. Spurious precision. And so what I said was, and in fact what we did in the book was I said we're not allowed to do that. What we have to do is this. We have to say, you sum it all together and you get about 1.3 billion. And what Tony said was, well, we can't do that because if we do that, then people will write and say you got your sums wrong. And Tony was right and I was right. This is the much better table, but a lot of people did write in and say we got our sums wrong, so you kind of have to be super careful. You all know about absolute versus relative risk. If a rate goes from 1% to 1.1%, that's a 0.1 percentage point increase, but it's a 10% increase. It's a 10% increase in relative risk, but only a 1 percentage point increase. But people don't understand it. Charts, Jesus Christ, junk charts. There's a great blog called Junk Charts. Don't use dual-axis charts. Don't use Bezos charts that don't have any numbers on them. Don't use non-uniform scales. Don't use unclear labels. Don't use unclear tick marks. Don't use false zeros. Don't use false colors. Don't use volumes and areas to represent things because people can't tell what the difference is between those things. Don't do graphs with no units. Don't put questionable lines of best fit on. Don't put them upside down. Do all the things that Edward Tufte says, annotate them and maximize data inc and minimize chart junk, and do direct labeling where you can and put error bars on. And actually, one of the things I don't agree is I don't understand what everyone hates about pie charts. If you're showing something that's supposed to add up to 100, a pie chart's something that people really understand. But anyway, use them if you like or don't. Put units on, zoom section scales, broken axes, whatever. For those of you who, I take it everyone said that this was the 2nd of December 2101 because that's the format string that I used. Give yourself give your neighbor a big hug if that's what you got. Here's a fantastic example of a dual-axis chart. So China's on the left axis and the US is on the right. See how terrifyingly China's spending's exceeded the US spending, except that actually the US spending is about 800 billions of constant 2020 dollars, and the Chinese stuff's about 250 billion. So it's like that's not really a very good chart. And here, unbelievably, like possibly the worst graph that's ever been produced in the history of humanity. Florida enacted a stand your ground law which said basically if you feel a bit threatened, just shoot the person and you'll be fine. I think that was roughly the summary. And unbelievably, someone produced this graphic for that in an attempt to demonstrate what a terrible law it was, and apparently his idea was that the red represents the blood flowing down, and you can see how much more blood there was after the stand your ground law was introduced. But I don't think that's how very many people will read that chart. So there you go. That's been me. I've got a website. I've got a blog. You can get the code from GitHub. You can mail me if you want. You can link to me if you want. There's a Slack group which is very quiet, but if you'd like to be part of it, it's likely I'll be doing a lot more because I might be writing a book on all this stuff. And I'm on Mastodon. I'm not on Twitter anymore because some bad stuff went on at Twitter. And that's me. Thank you very much for your patience, your attention. I'm sorry about all my ranting about things. I hope that was okay. Remember the Hippocratic Oath. It's not only for doctors, it's for everyone in this room. Well, possibly excepting the tech people, but it's basically everyone in this room. Thank you very much.
We do have time for some questions. We're going to try and get the mic around for the sake of people on screen and view.
Thank you so much for the speech. It was really interesting.
Thank you.
I have a question about the TDA
Yeah.
and automatic constraint generation. You said it supports Parquet files, right?
Parquet files, yes.
But does it support the nested schemas of the Parquet files? So let's say in your examples, it was just integers, strings, booleans, and so on. But in Parquet files, you can have arrays or arrays of objects.
No.
So does it input the schema and generate the constraint?
No, the only types it understands are Booleans, integers. It understands all the different types of integers, all the different types of floats. It understands dates and times. It understands textual data. It's okay with categoricals in Parquet, but that's all it understands at the moment. I may well extend that, though arrays would be a bit more complicated to work. I mean, structured data is more complicated to work with. It sort of relates actually to, you could do a lot of nice stuff with JSON as well, or structured data like that, but it's harder. There are JSON schemas that can sort of describe things, and is it called JPath or whatever the equivalent of XPath for JSON is? You can use that as well, but that's a much more complicated thing. So no, I'm afraid it doesn't. What it does do, you were the guy who was asking about DB2, weren't you? Is you can it actually also supports leaving data in some databases and generating queries to both generate the constraints and to verify data using the constraints. So it supports Postgres and MySQL and SQLite, and it supports Mongo a bit, though only simple data, basically tabular data in Mongo. And in fact, the version we're not going to talk about, the commercial version, supports some commercial databases, some other commercial databases as well. I can't remember whether it includes DB2, but it certainly includes Oracle and what's that thing Microsoft produced that they give the very confusing name? That one as well.
Okay, thank you so much.
Thanks.
Yeah, thank you for your presentation. I have a question about TDDA. With TDDA, do you have a way to define sort of threshold for the check? For example, I'm okay with all the numbers be positive, but like 5% of negative, I just want to.
Yeah, for most of them, there's not a way of doing that at the moment. You can specify a tolerance for floating point fields, which is not the same thing, obviously, but it's a bit connected. So it means that, so in particular then, if you generate the constraints automatically, and you don't want to say the maximum allowed value is 238.832, because that's a bit silly, you can say, well, allow 10% more than the training data or whatever. But no, apart from for nulls, where you can specify any number you like, it does have to be a count, not a percentage at the moment, though it would obviously be trivial to change that to a percentage. But there's not a way at the moment of, well, there's not a direct way of doing that. What you could do, having said that, I haven't really talked about this, but a very powerful thing to do, and actually what I think Great Expectations doesn't, I don't really want to knock Great Expectations, but they just come up with more and more, it's like there's this whole industry of writing more and more complicated kinds of constraints, whereas to my mind, what you should be doing is deriving new data sets from your original data sets and checking those. So a way of doing what you're talking about would be to measure it, take the BADS file, and then have a set of constraints on that that say if up to 5% of those, calculate the percentage, and then if up to 5% of those are bad, that's fine. So actually you could do it, you just have to work, it's not like natively supported in the library, you have to work slightly harder, but you're probably a developer, you can probably do that. Sure. I'm so glad both questions have started with, I want to ask you a question about TDDA. If you'd said like about my hernia or something.
I kind of feel like you just answered my question with the previous one, but are there any ways of defining your own constraints? Are there any other statistical kind of constraints that you
Yeah, okay, so yeah, those are two different things, obviously. In terms of defining your own constraints, the main way of doing, and what I do, and what I recommend is that basically, before feeding the data in, you define new columns that represent what you want, and then you either like build the column that is the check itself and just check that that's true, or you build some expression that is then suitable for one of the constraint types that it's got and use that. So that's very practical and it's quite easy, but it's not completely automatic. And then your second question was about statistical distribution. So there's a company called Evidently AI that focuses on data drift and distributions and so on. There's nothing directly in the TDDA library for looking at distributions, mostly because, to my mind, they're a slightly different thing. This is more about detecting clearly incorrect data than about detecting things that might or might not be. I mean, it obviously is still stuff that might or might not be wrong, but to my mind, there's a difference between a statistic being different and something hard like, it's being out of range or it's not matching the regular expression, all that kind of stuff. So you can obviously do it by computing those statistics and then putting limits on those. And on the one hand, I feel like it's a cop-out, and on the other hand, I feel like it's really sensible because it's not hard to compute those statistics and then put constraints on those. It's not hard to say, okay, I've got all this data, but I want to check it at store level as well, so I'll group it by store and write out a set of things and then check that all the stores are okay and stuff like that. But that's my answer, basically. If you want to do it, you would have to compute the statistics, put them in, and then probably the usual discovery will work fine on that statistic stuff, particularly if you then relax the constraints in the way I've talked about. Okay, well, I mean, I'm going to hang about, so if people want to ask questions one-on-one, or...
So, yeah, if you need questions...
I mean, in fact, I'm going to stay standing here, so if they don't turn the microphone off, But you're all free to go. Thank you very much for your time. Go